Welcome back to our study on the fundamentals of operating systems. This course is based on a text, Operating System Concepts, 10th edition, by Abraham Silberschatz, Greg Cagney, and Peter Galvin. I greatly appreciate the resources provided for this class by the authors and the publisher. We will be continuing now with Lesson 2, which is a continuation of our introduction to the course on operating systems. The fundamental goal of a computer system is to execute programs. Computer hardware is constructed toward this goal, and application programs are developed to use this hardware. These programs require certain common operations, such as those controlling input-output devices. The common functions of controlling and allocating resources are then brought together into one piece of software. You guessed it, the operating system. This explains that comment I made earlier about the programmer being able to spend time on applications themselves because he or she is no longer having to write the code to control those devices. We really have no universally accepted definition of what constitutes the operating system. One might say that it includes everything a vendor ships when you order the operating system. The features included, however, vary greatly across systems. Some systems take up less than a megabyte of space and lack even a full screen editor, whereas others require gigabytes of space and are based entirely on graphical windowing systems. For example, on your PC, Windows is a pretty large operating system, whereas Linux generally takes up less space. Of course, as you may know, there are several flavors of Linux, including Mac OS, and the size of the kernel will vary between the different versions. A more common definition is that the operating system is the one program running all the time on the computer. This program is usually called the kernel. I'm not sure definition is the right word because running all the time certainly does not define the operating system. It's just one characteristic of an operating system. In any event, as we will learn when we begin our study of the operating system memory manager, one of its responsibilities is to make sure that nothing intrudes on the memory space used by the operating system kernel itself. If that should happen, the computer operation will immediately come to a screeching halt. Along with the kernel, there are two types of programs. System programs, which are associated with the operating system but not necessarily part of the kernel, and application programs, which include all the programs not associated with the operating system itself. The matter of what constitutes an operating system became increasingly important as personal computers became more widespread and operating systems grew more sophisticated. That microcomputer I enjoyed in those early days used an operating system called the disk operating system. That was because operating the disk drives was most of its function. There were several flavors of disk operating systems, such as Apple DOS on the Apple II and Tris-DOS on the Tandy computers. CPM, which meant Control Program Microcomputers, was found on a number of different machines by different vendors. And of course there was PC-DOS, which came along with the original IBM PC. None of these operating systems actually managed a printer or a modem. When I added a new printer, for example, I would have to go into each application and configure the printer, and I would have to do that with every application that used a printer because the operating system did not perform that function. It was a real pain. Today, however, if I attach a new printer to the computer, my operating system will immediately recognize that it's there, and unless it's a brand new printer model, it will automatically add it to the system. From that point on, the user application, regardless of which one it is, will be able to use it without my having to perform any configuration measures at all. Even in the case of that brand new model, the printer vendor provides a configuration file that one can download and install to the operating system without the user having to perform any of that complicated configuration. Eventually, that new bottle will be added during one of the future updates of the operating system. In the 70s and 80s, the microcomputer operating systems of the time, Apple DOS, CP/M, and PC DOS, were primitive. The number of features constituting the operating system is increasing for mobile devices. Mobile operating systems include not only a core kernel, but also a middleware. A middleware, that's a set of software frameworks that provide additional service to application developers. For example, each of the two prominent mobile operating systems, Apple iOS and Google Android, features a core kernel along with middleware that supports databases, multimedia, and graphics, among other things. For our purposes, the operating system includes the always running kernel, middleware frameworks that ease application development and provide features, and system programs that aid in managing the system while it's running. Most of this unit is concerned with the kernel of general-purpose operating systems, but other components are discussed as needed to explain operating system design and operation. If you are following these lectures along with the book, we'll be skipping sections 1.2 and 1.3. These sections describe the physical characteristic of a computer, which you should already be familiar with from earlier entry-level courses. If you are not, it will be worth your while to read those two sections. An operating system provides the environment within which programs are executed. For a computer to start running, for instance, when it is powered up or rebooted, it needs to have an initial program to run. This initial program, or bootstrap program, is typically stored within the computer's hardware in firmware. You should recall that the physical memory that we use to load our programs and data is referred to as random access memory, or RAM. You may also know that there is another form of random access memory that has instructions actually burned into it. This is referred to as read-only memory, or ROM. ROM is part of the firmware, and normally it is where the bootstrap program is stored. You've seen how the lights on your computer and other connected devices light up when you initially start your machine. This is the bootstrap program testing to see what is there. In a modern operating system, if it finds something new, like you've added a new printer, it will automatically install and configure the new device. Since I'm sure most of you were not around when I was having to install new devices to those primitive operating systems, you cannot imagine how great that service is. It initializes all aspects of the system, from CPU registers to device controllers to memory contents. The bootstrap program must know how to load the operating system and how to start executing that system. To accomplish this goal, the bootstrap program must locate the operating system kernel and load it into memory. There is special memory on your computer system board that contains data that is supported by a small internal battery. This memory is usually referred to as CMOS, and the data contained therein is called the Basic Input-Output System, or BIOS. This is where the system keeps that configuration data used for the bootstrap program for startup. It also contains a boot sequence, which tells the computer the order that storage devices should be searched to find that operating system. So after all testing is done, your operating system will be loaded. Once the kernel is loaded and executing, it can start providing services to the system and its users. Some services are provided outside the kernel by system programs that are loaded into memory at boot time. These become system daemons, which run the entire time the kernel and therefore the system is running. On Linux, the first system program is systemd, and it starts many other daemons. Once this phase is complete, the system is fully booted and the system waits for some event to occur. If there are no processes to execute, no input-output devices to service, and no users to whom to respond, an operating system will sit quietly waiting for something to happen. Events are almost always signaled by the occurrence of an interrupt. Let me try to give you a brief explanation of interrupts. Let's say that you have an operating system that assigns tasks to multiple devices as operating systems do. How does it know when each device needs further attention? Well, it could use a technique called polling. P-O-L-L-I-N-G, polling, where it simply asks each device in turn if it needs anything. That would be pretty simple to implement, and it would be fair. So what problem do you see with that polling approach? The problem is if the device doesn't need service, the system has just wasted a CPU cycle polling. In fact, most of the time that answer would be no service needed, which means a lot of cycles would be wasted with all this asking. That's kind of like the kids in the back seat of the car saying time after time, "Are we there yet?" A much more efficient approach would be to use the interrupt. In the interrupt approach, once the operating system has assigned a task to a device, it simply waits until the device says it's finished. It doesn't bother with it until then. Of course, we would need a program to handle these interrupts, but the result would be a much more efficient way to manage the resources. The operating system assigned a task to a device, and when the device is finished, it interrupts the CPU to let it know that the task is complete. Another form of interrupt is a trap or an exception, which is a software-generated interrupt caused either by an error or by a specific request from a user program that an operating system service be performed by executing a special operation called a system call. That could be that printer informing the operating system that the job was complete. One of the most important capabilities of operating systems is the ability to run multiple programs. Multiprogramming is the technique of utilizing several programs concurrently in a single computer system. A single program cannot normally keep either the CPU or the I/O devices busy all the time. Furthermore, users typically want to run more than one program at a time as well. Multiprogramming increases CPU utilization as well as keeping users satisfied by organizing programs so that the CPU always has one to execute. In a multi-programmed system, a program in execution is called a process. The operating system keeps several processes in memory simultaneously. It picks a process and begins to execute. Eventually, the process may have to wait for some task, such as an input-output operation, to complete. In a non-multi-program system, the CPU would sit idle. In a multi-program system, the operating system simply switches to and executes another process. When that process needs to wait, the CPU switches to another process, and so on. Eventually, the first process finishes waiting and gets the CPU back. As long as at least one process needs to execute, the CPU is never idle. I recall in those early days occasionally having to print long reports. Because this was before multi-programming, once I pressed the print button, I would have to wait until the entire report was completed before using the computer again. Also, let me use this opportunity to give you a little preview of the issues we'll be studying as we work on in the course, including what most refer to as the various operating system managers. First, if there are multiple programs running at the same time, those programs must have its own memory, and that area of memory cannot be used by any other process. The memory manager handles that. Second, a process will need at least occasionally to use the CPU. The processor manager is responsible for that. If multiple processes are running, no large process can be allowed to starve out all the rest, even the smallest jobs, so they must take turns using that CPU. The process manager is responsible for that. If in fact one of those processes needs to send output to the printer, it must call for it, and the device manager takes care of that. If any of those processes need to read from or write to a file, it must know where to find the file. It must have permission, and it must know how to get it from storage. That's the responsibility of the file manager. So you see, we're going to be learning about the responsibilities of at least 5 different operating system managers, or 5 different management systems within the operating system. Well, that was a pretty good lesson. Let's take a break now, take care of any business that you have to do, look over your notes, and when you're ready, come on back and we'll continue to lesson 3 in our introductory overview of the course.